Welcome to Giang Mystery Hub, where today we journey into the theoretical abyss to uncover objects that truly defy imagination. We know black holes exist, but mathematics suggests there are stranger monsters hiding in the dark equations of physics. These are theoretical black holes, objects that have not yet been seen but exist within the complex laws of relativity. From objects smaller than an atom to giants that devour stars from the inside, the universe is full of mysteries. Join us as we explore 9 theoretical black holes that challenge everything we think we know about space and time. Our journey begins at the very beginning of time, moments after the Big Bang, where chaos reigns supreme in space. Primordial black holes formed immediately after the creation event, born from chaotic density fluctuations rather than the collapse of stars. These ancient entities can be incredibly small, some no larger than a single atom, yet possessing immense gravitational power. Despite their microscopic size, a single primordial black hole could contain the entire mass of a giant mountain range. They might be wandering through our universe right now, completely invisible to us, hiding the secrets of the early cosmos. Due to their small size, they emit Hawking radiation rapidly, potentially evaporating in a flash of high-energy gamma rays. As the universe cooled down, the first stars began to form, leading us to our next theoretical cosmic monster. Meet the quasi-star, a hypothetical type of extremely massive star that may have existed very early in the universe. Unlike normal stars, a quasi-star contains a black hole at its core, slowly devouring the star from the inside out. The energy generated by the black hole feeding on the star prevents the outer layers from collapsing under gravity. This delicate balance creates a celestial body larger and brighter than anything we observe in the modern universe today. Eventually, the black hole wins the battle, consuming the entire host star and leaving behind a supermassive black hole. These ancient cannibals might be the seeds that grew into the supermassive black holes at the centers of galaxies. Now imagine creating a black hole not from matter, but from pure energy using advanced technology of the future. This is the concept of a Kugelblitz, a black hole formed from radiation so intense it warps space-time itself. According to general relativity, if you concentrate enough light into a small space, the energy density creates an event horizon. Scientists theorize that a controlled Kugelblitz could one day serve as the ultimate power source for interstellar starships. The temperatures required to create such an object would be hotter than the universe was moments after the Big Bang. However, maintaining such a dense concentration of energy is currently beyond our capabilities and defies our engineering limits. Next, we encounter the Gravastar, an object proposed as an alternative to black holes without the problematic singularities. A gravastar consists of a shell of ultra-dense matter surrounding a core of repulsive dark energy that prevents collapse. Unlike a black hole, there is no singularity where physics breaks down, just a vacuum of exotic dark energy. Anything falling onto a gravastar would smash into its hard surface shell, releasing energy rather than vanishing forever. Astronomers hope to distinguish gravastars from black holes by analyzing the unique gravitational waves they emit during mergers. The shell is incredibly thin but nearly indestructible, suspended perfectly between the crushing gravity and the internal repulsive force. Moving deeper into quantum theory, we find the Planck star, a solution to the paradox of the singularity. Loop quantum gravity suggests that matter cannot be compressed infinitely, so the collapse stops at the Planck density. Instead of collapsing forever, the star bounces back, creating a massive slow-motion explosion that lasts for billions of observer years. Due to extreme time dilation, this bounce happens instantly for the star, but takes the age of the universe for us. Eventually, as the black hole evaporates, the Planck star inside might finally reveal itself to the outside universe. Some scientists speculate that mysterious fast radio bursts could actually be the signals of dying Planck stars exploding. String theory offers us perhaps the strangest candidate of all, the fuzzball, a black hole that is not empty. According to this theory, a black hole is a tangled ball of strings, like a giant cosmic ball of yarn. There is no sharp event horizon or singularity. Instead, the entire volume is filled with these fundamental vibrating strings. Anything falling into a fuzzball isn't lost to a singularity, but is preserved as information on the object's surface, This elegant theory solves the famous information paradox, suggesting that data is never destroyed, just scrambled into strings. If fuzzballs exist, the interior of a black hole is a physical structure we could theoretically touch and measure. Now, let's reverse the film of gravity and time to encounter the opposite of a black hole, the white hole. A white hole is a region of space-time that cannot be entered from the outside, only ejecting matter outward. While a black hole lets nothing escape, a white hole lets nothing enter, acting as a cosmic one-way street. Some theories suggest that every black hole is connected to a white hole, possibly in a completely different universe. Matter swallowed by a black hole might travel through a wormhole and erupt from a white hole somewhere else. White holes violate the second law of thermodynamics, making them highly unlikely to exist in our current stable universe. Next, we explore the charged black hole, a monster that carries a massive electric charge alongside its gravity. Unlike standard black holes, these possess two event horizons, creating a complex internal structure known as the Cauchy horizon. The electromagnetic repulsion is so strong it could tear atoms apart long before they cross the point of no return. If the charge is strong enough, it could theoretically balance out gravity, creating a naked singularity without a horizon. In reality, these are rare because they would quickly neutralize themselves by attracting oppositely charged matter from space. However, the unique geometry inside might theoretically allow for a stable passage to other regions of space-time. Finally, we arrive at the most terrifying possibility: the naked singularity, a glitch in the fabric of reality. Imagine a black hole spinning so fast that it sheds its event horizon, leaving the singularity completely exposed to us. Without an event horizon to hide it, the breakdown of physics at the singularity would be visible to the universe. This would violate the cosmic censorship hypothesis, which states that singularities must always be hidden from outside observers. If naked singularities exist, they represent a total failure of our ability to predict the future evolution of the universe. Computer simulations suggest they might form under specific conditions, challenging the very foundations of Einstein's general relativity. From the microscopic primordial holes to the naked singularities, these objects push the boundaries of human knowledge and imagination. While some of these may remain purely mathematical, others might be waiting to be discovered by future astronomers. With advanced telescopes and gravitational wave detectors, we are getting closer to unveiling the true nature of these monsters. The universe is far stranger than we can imagine, and black holes are the keys to unlocking its deepest secrets. Understanding these theoretical objects brings us one step closer to the ultimate goal: a unified theory of everything. Which of these theoretical black holes do you think is most likely to exist in our vast universe? If you enjoyed this journey into the unknown, make sure to subscribe and hit the bell for more mysteries. Thank you for watching Giang Mystery Hub. Keep looking up and never stop questioning the nature of our reality.